mentioned earlier, this is our z node and this is our radius. So we got our circular locus to be defined by z minus 3 plus 4i equals to 2. So for the Cartesian expansion, we let z to be x plus yi, and after expanding and substituting everything, we got our final locus equation to be x minus 3 squared plus y minus 4 squared equals to 4. This is actually a circle equation which gives us a circle at center 3, 4 and radius of 2. Now moving on to the modulus extrema. So this is our circle, and as you can see, there's a green line which crosses the origin and the center of the circle. So this point right here is actually called the z-min, which is the closest point from the origin to the circle, and the z-max is oppositely the furthest point from the origin to the circle. So this green line is denoted by y equals to 4 over 3x, where the 4 over 3 is actually the gradient of the green line. So now we have these two equations right here, the straight line equation and the circle equation. When we solve the simultaneous equation between these two, we will get two different intersection points, which corresponds to our z-min and z-max value. After doing all of the work in here, we got our z-max complex number to be 21 over 5 plus 28 over 5i, where our z-min complex number is 9 over 5 plus 12 over 5i. So to prove these two equations generally, z-min, as we all know, is the shortest distance between the origin and the circle. So when we start at the center of the circle, we have to move back towards the origin. So that's why we have to minus the radius. But we have to multiply the radius with the unit vector to get the direct diagonal component of the radius. Because if we don't, we will get a separate horizontal and vertical component of the radius. Same goes to z-max. When we start at z node, so we have to move further up. So we have to plus r times the unit vector to get the direct diagonal component. When I substitute the values inside the formula given to prove, we actually got the exact same values as when we solved the simultaneous equation just now. Hence, it is proven. Now, for the argument extrema, this is a new diagram of our circle where I have drawn two separate lines which acts as a tangent for the circles. So by having two lines, we actually have two different angles starting from the x-axis to the first line is actually the smallest angle, which we call it as a minimum argument, and from the x-axis to the further tangent line is actually called the maximum argument. And when we substitute y equals to mx inside the circle equation, we'll get a third equation. So what is the relationship between the straight line and the circle? It is actually a tangent. When a line crosses one point of the circle, the discriminant is actually 0. From the third equation that we obtained just now, we extract the a, b, and c values back to the discriminant equals to 0 formula. We got m to be 4.23 and 0.57. We have two tangents with two different gradients. So after we get our m values, we can solve for x and y for each tangent. So we substitute the m values inside the third equation to get x. So when we got x, we will substitute it back into the y equals to mx to get y. For the gradient of m equals to 4.23, which is the further tangent up there, we get the x value to be 1.05 and y value to be 4.44. So to calculate the maximum argument, we use the formula tangent inverse equals to y over x. So when we plug in the formula, we will get the maximum argument to be 76.69 degrees. So on the other hand, for m equals to 0.57, which is the lower tangent line, when we substitute it back into the third formula, we got x to be 3.99 and y to be 2.27. So when we substitute to find the minimum argument, we got that the minimum argument is 29.64.
Let's justify the modulus and argument extremas for a circle using the sweeping circle and tangent ray methods. As you can see from this picture right here, we have two sweeping circles and a locus. These two sweeping circles here are centered at the origin. This blue dashed line here represents the sweeping minimum circle. When our z-min is 3, this circle here first touches the locus at point 1.8 and 2.4, and for the red dashed line here represent the sweeping maximum circle, because as we expand our radius to 7, our locus is perfectly inscribed within the circle, which marks our z-max to be at point 4.2, 5.6, which has been denoted as z-max. Now for the argument part, we have two lines right here, orange and green lines. So the orange and green lines here represents the tangent to the circle. So the orange line here represents y equals to 0.57x, whereas the green line represents y equals to 4.23x. So these two lines right here are the tangent to the circle, which we justify by showing it is 90 degrees between the rays and the radius of this intersection point, which is 1.05, 4.46.
My ellipse has at negative 2, 0 and 2, 0 with a constant sum 6, starting from modulus z plus 2 plus modulus z minus 2 equal to 6. I isolate a square root, square twice, and simplify. After cancelling and rearranging, I get x squared over 9 plus y squared over 5 equal to 1. This ellipse is centered at the origin with semi-major axis 3 horizontally and semi-minor axis 5 vertically. To find mean and max distance from the origin, set d squared to x squared plus y squared. Implicit differentiation of the ellipse give dy dx equal to negative 5x over 9y. Setting d squared over dx equal to 0 leads to x equal to 0. Then the ellipse give y equal to plus minus 5 with distance 5. Also check y equal to 0 give x equal to plus minus 3 with distance 3. So minimum modulus is 5 and z equal to plus minus I 5. Maximum is 3 at z equal to plus minus 3. For argument extrema, substitute y equal to mx into the ellipse, we get x squared 1 over 9 plus m squared over 5 equal to 1. The discriminant is 4, 1 over 9 plus m squared over 5. Setting it to 0 gives m squared equal to negative 5 over 9. No real solution. This means that origin lies inside the ellipse. Every line through the origin cuts the ellipse twice, no tangent from the origin. Therefore, every angle from 0 to 2 pi occurs, or 0 degree to 360 degree. The smallest principal argument is 0, which is at z equal to 3. The largest approaches is 2 pi. In summary, ellipse x squared over 9 plus y squared over 5 equal to 1, and modulus z minimum is set 5 at plus minus I set 5, and modulus z max equal to 3 at positive negative 3. Arguments cover all angles because origin is inside. That's the complete solution.
Now, let's justify the modulus and argument extremas for an ellipse using the sweeping circle and tangent rays methods. Since our ellipse is centered at the origin, the sweeping circle is simple. The minimum modulus is the semi-minor axis, so 5, and the maximum is the semi-major axis, 3. For the ellipse, we justify the argument extrema using the discriminant method. When we substitute y equals to mx into the equation, we find that m squared equals to negative 5 over 9, and since m has no real solutions, this proves that the origin lies inside the ellipse. Unlike the circle, there are no tangent rays from the origin because every line cuts the ellipse twice. Consequently, the argument is unrestricted, spanning a full rotation from 0 to 2 pi. We justify the z-mean at 0 located at the vertex of 3, 0.
That's all from us. Thank you!